All right, let's just skip the basic Hello World tutorials today. If you're already perfectly comfortable with RAG and Azure Basics, well, you are exactly where you need to be. Today, we're going to break down the really rigorous, deliberate engineering decisions that you actually need to build robust, production-ready enterprise search architectures on Azure. We're not just going to click around a portal for the sake of it. We're going to understand exactly why these configuration options exist in the first place and really dig into the engineering trade-offs behind every single choice.
Here's our roadmap for this explainer. First, architecting your vector service. 2. Ingestion and integrated vectorization. 3. Chunking strategies and trade-offs. 4. The multi-layer retrieval pipeline. 5. Breaking down reciprocal rank fusion. And finally, number 6, we'll look at scaling to 1 million documents. Let's just dive right in.
Section 1. Architecting your vector service and choosing the right foundation. So right off the bat, we have to ask, why use Azure AI Search over traditional databases? It really comes down to your system requirements and specific workloads. If you're dealing with highly mutable, real-time data where updates have to be searchable instantly, Cosmos DB is a fantastic NoSQL choice. If you absolutely require ultra-low latency, in-memory caching for user sessions, Azure Managed Redis is your go-to. But when your enterprise application demands deep, unstructured indexing with out-of-the-box semantic re-ranking and a dedicated engine for true hybrid search, Azure AI Search is the absolute powerhouse you need.
Now, at the very core of vector search are your approximate nearest neighbor, or ANN, algorithms. And you definitely don't want to just blindly pick one of these. Selecting an index strategy depends entirely on your query volume and your available memory. Disk-and is phenomenal for massive data sets, mostly because it saves compute resources by reading from disk while still maintaining accuracy. HNSW, on the other hand, is a bit of a memory hog, but it excels in lightning-fast query responses. And IVF-flat, well, that's really your fallback when hardware is strictly limited. The choice you make here directly dictates your baseline latency and your infrastructure costs.
Moving on to Section 2, Ingestion and Integrated Vectorization, basically automating the data pipeline.
Historically, engineers had to build incredibly complex external middleware just to move documents from blob storage, crack them open, chunk them, embed them, and push them to an index. It was a lot. But by leveraging Azure AI Search's integrated vectorization, we literally eliminate the need for that separate pipeline. The native indexer completely automates the retrieval, document cracking, AI enrichment, text splitting, and vector embedding in a single, resilient workflow with built-in retry logic. Honestly, it's a massive reduction in operational overhead.
But what happens when your data isn't just text? If you're building multimodal search scenarios, let's say you're analyzing complex PDFs full of diagrams, knowledge store projections are absolutely critical. They allow your automated pipeline to extract those images and structural metadata during the cracking phase and physically save them directly back to Azure storage as objects or tables, meaning your downstream applications can just reference the actual images at query time without ever having to reprocess the source document. It's a real game changer.
Section 3. Chunking strategies and trade-offs. Let's do some retrieval math.
If you've ever wondered what the optimal chunk size actually is, Microsoft's rigorous benchmarking data reveals a bit of a magic number. Across a massive variety of query types, 512 token chunks with a 25% overlap consistently outperform other configurations. Going much larger than this actually degrades your performance. Why? Because your embedding models are forced to compress way too much semantic density into a fixed dimensional vector space, which just waters down the entire meaning.
So the crucial takeaway here is that you must avoid the anti-pattern of arbitrary, blind text splitting. Think about it. If you split a chunk right in the middle of a sentence, you completely destroy the semantic context for both the end of the previous chunk and the beginning of the next one. It is an absolute nightmare to try and debug in production at 2 a.m. By using the text split skill or document layout parsing to preserve sentence boundaries, you prevent that semantic fragmentation. This single configuration change will drastically improve the quality of your vector embeddings.
Section 4. The multi-layer retrieval pipeline. Time to go beyond basic vector search.
This is a question literally every AI engineer faces at some point. A lot of developers make the early mistake of relying solely on vector retrieval. And sure, it feels like magic at first. But as user questions scale into production and become highly specific or really nuanced, vector-only systems inevitably leave relevance on the table. They start hallucinating connections, or they just totally miss exact terms.
To fix mediocre retrieval, we really have to respect the unique strengths of different search paradigms. Vector similarity gives us amazing conceptual recall, finding mathematically similar meaning even if the user typed in a completely different vocabulary.
But BM25 keyword search, that provides absolute precision. It excels at exact matches, specific product codes, highly specialized enterprise jargon, dates, things that vectors often just blur together. We absolutely must combine them.
Combining those paradigms builds an incredibly powerful three-layer pipeline. Layer 1 is hybrid search, which is blending that BM25 and vector. Layer 2 applies semantic re-ranking, where we use a deep transformer model to rescore those top results based on actual machine reading comprehension. Think about it. In a pure vector search, the absolute best result for a query might initially sit down at position 8. But when you layer on hybrid keyword matching and semantic ranking, that perfect document gets pushed all the way to position 1.
And for the most demanding enterprise workloads, we introduce Layer 3, agentic retrieval. By utilizing the knowledge-based object in the Preview API, this layer literally intercepts complex, multi-part questions from users, automatically decomposes them into multiple distinct subqueries, runs those all in parallel, and then merges the results. Yes, it adds minor latency, but Microsoft's benchmarks show it can improve answer quality by up to 40% on difficult queries. For sure, worth the trade-off.
Section 5, Reciprocal Rank Fusion, explained. Let's talk about harmonizing those results.
So when you run a hybrid query, you're getting a list of BM25 scores and a totally separate list of vector distance scores. They are on totally different scales. You obviously can't just add them up. Enter Reciprocal Rank Fusion, or RRF. What makes RRF so incredibly powerful is that it's a zero-tuning mathematical method. It completely removes the engineering headache of manually figuring out linear combination weights. Instead, it uses a rank constant to determine how much influence documents retain strictly on their relative position in each independent list. This guarantees a fair weighting across completely different algorithms.
Let's make this concrete. Imagine a scenario where Doc 4 is a perfect keyword match, ranking number 1 in BM25, but the vector search didn't even find it. Meanwhile, document 3 performed incredibly well in both, ranking number 1 in vector and number 2 in keyword. RFF mathematics naturally rewards that consensus. You can clearly see how document 3 bubbles up to the absolute top spot for the final harmonized rank, which provides a way more relevant result than either algorithm could ever achieve on its own.
Finally, Section 6, Scaling to 1,000,000 documents. Basically what happens when RAG hits a wall.
Because when RAG hits that wall, you experience what we call entropy growth. Token-based chunking causes your chunk of volume to aggressively outpace your document count. Suddenly, you have 1,000,000 documents turning into tens of millions of chunks, and it creates an incredibly dense, noisy vector space. The curse of dimensionality sets in, and those nearest neighbor distance metrics, they just begin to lose all meaning. To survive this, you have to shift away from blind text splitting and fully embrace structural retrieval. That means semantic chunking, deduplication, and hierarchical indexing to preserve logical boundaries and finally cut through the noise.
To manage all that noise, Azure gives you a strictness style. By adjusting this parameter on your data source integration, you can aggressively filter out irrelevant or borderline chunks before they even get close to the LLM prompt. If your application handles precise factual lookups or super strict compliance data, cranking that strictness up to a 4 or 5 ensures that only highly relevant, undeniable matches actually make it through the pipeline.
But listen, strictness is just one dial. To make latency predictable and really control costs at a massive scale, you must apply core distributed systems principles. You have to enforce metadata filtering to narrow that candidate search space before the vector math even runs. You need to implement partitioned indexes. You absolutely must establish caching strategies for frequent queries so you aren't hitting the engine twice. And crucially, especially for enterprise security, you must ensure your Entra ID access control lists and Microsoft Purview sensitivity labels flow all the way through, meaning users only ever retrieve vectors they're actually authorized to see.
At the end of the day, building search isn't just about casually feeding a bunch of PDFs to a language model. It requires rigorous, layered engineering. So I'll leave you with this final thought. If your RAG system works with 1,000 documents, you've successfully validated an idea. But if it works seamlessly with 1,000,000 documents, you've respected theory and you've built a true architecture. So ask yourself, are you just validating ideas right now? Or are you ready to engineer a truly scalable search platform? Keep exploring, keep building, and I will see you in the next explainer.